Hi, I'm Sala. In this video, we'll discuss a case study on guaranteeing robust performance for this simple second plant. In this first video, we'll address just a simulation-based approach for a given pre-existing controller, a PID, and we'll discuss the advantages and drawbacks of that simulation-based approach. So, in a forthcoming video, we'll address how to obtain performance certificates, robustness margins, using H-infinity norms and H-infinity controller design. In this first video, we'll discuss these issues in here. So, the plant model is 5 divided by s plus 1 squared, and we will imagine that we have an additive unstructured error bound of 0.2. This will be our model, but adding delta will confirm the true plant under this assumption of additive modeling error. The robust control toolbox can generate, with this command, uncertain linear time invariant dynamics. Norm 1 uncertainty, the system generated by the blue command, is something with a random both diagram with random phase and amplitude between 0 and 1. So if I multiply it by this bound delta, then this is an unstructured uncertainty of size 0.2. This normalization of the uncertainty is important in theoretical developments. So instead of having this delta of size 0.2, we are equivalently representing it by a standardized delta less than 1. Scaling to 1 the things we wish is kind of common practice in robust control, with no loss of generality. So we have that thing, and we can simulate it. MATLAB Robust Control Toolbox, when I wish to compute the time or frequency response of these uncertain systems, just throws the dice and gets a bunch of random plants under this maximum amplitude bound. So for instance, here we have this step response, and if I ask for the magnitude both diagram, then we get this blue set of frequency responses. As you can see, the frequency response can be constant at high frequencies, which means that we may have a direct input-output coupling. Here we have it, up to size 0.2, because, well, this delta can be just a static gain with instant response. As I am going to carry out a simulation-based analysis, if I add this extra low-pass filter, this thing has 33 radian seconds bandwidth, so we kill the high frequency uncertainty from this frequency onwards. And if I simulate again, then now all the plants start in 0 and take a few cents of a second to depart from 0. This is the step response. And in both diagram, my low-pass filter kills the possible uncertainties from this frequency onwards. So the yellow line depicts the constant 0.2 uncertainty at all frequencies in logarithmic decibel scale. And now I have added this low-pass filter in there, saying that sooner or later the actual frequency response of my physical plant will diminish in my simulations. So we'll keep it like that, at least for simulation, in this generation of G2. In summary, we saw how to generate a model with additive uncertainty with some kind of reduction at high frequency, and we have shown the step response of my family of plants, throwing the dice on the uncertainty by the robust control toolbox, and the both diagram, in which we see sort of an envelope of uncertainty, in which I have sort of 4% uncertainty at low frequency, 0.2 over 5 is 4%, and at high frequency I have like an envelope in which all the uncertain plants can be inside this region. Okay, I actually did cut the high frequency like this. So once we have our model, then let us assume that, as it's usual in undergraduate courses, we design a PID based on maybe, trial and error, based on my nominal model, this G. So in an undergraduate course, if my simulation on this G is good, then usually we say that the design is finished. However, we need to validate it, at least in simulation, in the face of modeling errors. So let's do it. This CL_num stands for the nominal closed loop, from reference to output. So here we have a nice response, let's say, in which the open loop response, step of 1 over the DC gain so that it ends in 1. That open loop settling time, around 6 seconds, is accelerated almost 3 times until 2.5 seconds, let's say, rise time, and we are happy with this performance. If we wish to have a look at the error signal, this feedback command builds the setpoint to error closed loop transfer function, and the step response nominal is just like the output, but instead of going from 0 to 1, the error goes from 1 to 0. But usually what we wish when we look at the error is to look at the magnitude bow diagram. Here we have it, and it's the usual high pass shape in which the error is small at low frequencies. Of course, we have integral action, so the error goes to 0 at 0 frequency, and then we have a set of frequencies in which control is not effective. This bandwidth depends, of course, on the PID tuning, and this is it. Following a given set point is progressively more difficult as the frequency increases until control does nothing, or when it is above 0 dBs, it does worse than nothing. It amplifies the error. But okay, we think that the bandwidth of this is in frequency is reasonable. We are happy with the time response. And last, if we have a look to the closed loop transfer function between setpoint and manipulated variable control action, then this step response is like this. Gain is 5, nominal, so it ends in the inverse of the gain. And initially, this PID proposes a 10 times manipulated variable overshoot, kind of boost of 10 times at initial phases of the transient, so that we quickly push our control variable upwards. Well, maybe that 10 times boost, it's sort of excessive. Well, that depends on my applications and on my saturation limit, but okay, for the moment being in this problem, we'll consider it satisfactory, and that boost also can be observed in the both magnitude plot, because we have the inverse of the gain here and the boost of 20 dBs from -14 to +6 at high frequency. Nevertheless, we are happy with this. If there is no high frequency noise to be amplified, so that we might need to change this, but okay, we are happy. So regarding robustness, we can simulate the same closed loop functions, but instead of with the nominal G, with the true actual plants with modeling errors, so MATLAB throws the dice and generates a family of random plants to simulate. Well, this feedback of G true, okay, gets me this step response, and okay, we have this kind of high frequency dynamics we were expecting, but we understand robust performance in the sense that, okay, except in the first quarter of a second, all of the closed loops have the same final value, integral action, they go to 1, and roughly the same, settling time, overshoot, and all things that the PID control designer usually looks for. Then this kind of simulation, it's what we understand technically as robust performance. If we are not interested on the stuff we have in this initial phase, okay, we see that our PID has successfully swallowed all the modeling uncertainty and all simulations look basically the same. Good, this is robust performance. And if we see it in the frequency domain, this is the error, the set point to error closed loop. Well, we see that up to this frequency, all the both plots are roughly the same, and that we have this kind of high frequency resonances. So the effect of the uncertainty with this controller is basically here. These are the high frequency stuff corresponding to the initial states of the time response, but roughly at frequencies when control is effective, all the loops behave the same. So this is robust performance in the world of frequency response, saying that, for instance, all the loops have an error figure below this red line. Last, control action, this feedback. Well, we see also this kind of robust performance. All random plans result in more or less the same sort of behavior of the control action, both in time and in frequency. Okay, we have kind of oscillations here, but if we think these are reasonably close to the red thing, and in general error control action in time and frequency, if we think that everything is close enough to the nominal simulation, then we validate our design by simulation and we assert that it seems that we have robust performance. However, let us end the video with some remarks. First, we do not have any theoretical justification on why we did achieve robust performance. Maybe we were just lucky and another random dies. Maybe it generates a plant in which the closed loop is unstable. So, in some sense, we are happy because simulations seem to be good enough, but we should have also a kind of theoretical guarantee of robust stability or robust performance. So this is the first drawback. It seems to work, but we don't know if the next random simulation will work or not. Second issue is that we have no clue on how to improve the performance if this PID did not have enough robustness. How can we retune the PID? So we need kind of theoretical insight on this robust performance stuff to guide design modifications. So these are the two drawbacks that call for some theoretical analysis of robust performance. But on the other hand, it's important to stress that simulation-based performance validation is of paramount importance in practice because, we usually can have complex models of a petrochemical plant with lots of nonlinearities, high order simulations, even, finite element approximations of partial differential equations, fluid dynamics, etc. And so extracting out that complexity in just an delta like this and bounding its size, it's kind of a difficult exercise. So on one hand, if we succeed in extracting the uncertainty like this, then we can have mathematical guarantees based on theory we'll see in other videos. But on the other hand, extracting that delta from a computational fluid dynamics simulator or non-equilibrium chemistry, etc., it's kind of a difficult task. And also maybe the theory can be, conservative in the sense that the theory of robust control gives sufficient conditions for stability, but maybe in some cases they are too conservative for a particular kind of uncertainty in mechanical systems or chemical systems or the like. So at the end, we need theory to exclude the possibility of seeing nice simulations because of good luck. And on the other hand, we need simulation-based validation in actual applications in which we have a model with a high accuracy, so we can assess whether simplifying such a high complexity to 5 over s plus 1 squared was actually wise or not. So this is it. We'll see the formal approach to robust performance in forthcoming videos. Now we end this one here. Thanks for watching.